welcome back to the lecture series of finite volume. Now, this error when you use for the to reduce the streamwise diffusion or the higher order profile, these are also called the dispersion error. Now dispersion error actually shows some this kind of small oscillation in the solution, and this is because of the at the presence of large gradients which rendered to the solution unbounded. Now, if you have this higher order profile, then you get this kind of thing. So, now if you move to this shows an profile which actually, now this is the dispersion error causing oscillation in presence of large gradient. So, that is what happens. Now, one can evaluate this error by some sort of a simplified version of the equation system. Let us say in 1D, if you assume this is my unsteady scalar transport convection equation, then the exact solution would be phi x t equals to phi t e to the power j k x, where j is -1 and the exact value of the gradients become del x of phi x t equals to j k phi t e to the power j k x, which is j k phi x t. Now, with the interpolation profile, the numerical approximation of the gradient which is written in terms of phi at locations, let us say minus m delta x, minus m plus 1 delta x, and so on, like delta x 2x delta x, like that. Then one can write del x of phi x t equals to 1 by delta x summation of n equals to minus m a n phi x plus n delta x t, which is nothing but 1 by delta x n equals to minus m n a n phi t e to the power j k x plus n delta x. Now, we substitute this of the assumed solution becomes del x of phi x t equals to or equivalent to 1 by delta x summation of n minus m to n a n phi t e to the power j k x plus n delta x, which one can write 1 by delta x summation of n equals to minus m by n a n e to the power j k n delta x phi x t. Now, this is our exact solution, this is our exact, this is our approximated solution. Now, if you compare both of them together, one can find k equals to minus j delta x summation n equals to minus m to n a n e to the power j k n delta x. Now, what you can get is that k is essentially an imaginary number. So, k is an imaginary number. So, since k is imaginary, it will have two component, one is real plus one is imaginary. So, it will be having two component for this value k. So, now one can think about writing that real k plus imaginary part of the k. Now, insert this k in the exact solution. So, k in exact solution, which you get then phi x t equals to phi t e to the power j k x equals to phi t e to the power j r e k plus j imaginary k x, which will become phi t e to the power j r e k into e to the power minus imaginary k x, because this will multiplied with j and j square. So, j square is minus 1. So, if you look at the numerical solution, it may include both the term. That means, it may include both diffusion and dispersion. So, the numerical solution can have both the term. So, the diffusion which will make the solution diffusive in nature and dispersion which will lead to some sort of an small oscillations in the at sharp gradient. So, either of these cases there are certain issues. Now, if you say k is real, if k is real, then this portion of the term goes away. So, there is no imaginary component. So, the solution would be only this much. So, the error which will actually present there, it is only dispersion error. So, if there is no imaginary part, if k is real, then only dispersion error occurs. Okay. However, if k is complex, that means it will have both real and imaginary part, then this will have both the errors occur, okay, or will arise. So, based on this analysis, now one can have a value for k for different scheme. Now, k could be different for upwind scheme, k could be different from other scheme. So, now let us say if you look at k for upwind scheme, you consider upwind scheme and try to find out the value for k. So, in upwind scheme what we have, del phi by del x, what is that, del phi e minus phi w by delta x, which is phi c minus phi big capital W by delta x. So, one can write that is e to the power j k x minus e to the power j k x minus delta x divided by delta x phi x t, which will get you back 1 minus cos k delta x plus j sin k delta x divided by delta x phi x t. So, now that this is j k phi x t, so which will be, so this is equals to j k phi x t. From here one can think about the k is sin k delta x divided by delta x minus j into 1 minus cos k delta x divided by delta x. So, it is clear that in the upwind this is your real part, this is your imaginary part. So, that clearly shows that in upwind scheme you will have both real and imaginary component, that means both kind of error, which is diffusive and dispersive, they will arise. Now, at the same time, if you look at CD scheme, the del phi by del x would be phi e minus phi w by delta x, which is phi e minus phi w by 2 delta x, which one can write e to the power j k x plus delta x minus e to the power j k x minus delta x divided by 2 delta x phi x t. So, essentially this will become 1 by delta x j sin k delta x phi x t, where equals to j k phi x t. From this one can get k equals to sin k delta x by delta x, which is only real component. So, only real component of the system. So, the real component if it is there, then that means the CD shows only dispersion error. So, that is what is important, that in one case there will be both the errors present and the other case. So, this dispersion error actually causes some sort of an oscillation and undershoot and overshoot of the results at the location where you have sharp gradient. Now, once we have some sort of an or having an idea about this kind of different errors, numerical dispersion. So, it is quite desirable to develop some sort of a scheme or convective discretization scheme which are non-oscillatory and higher order accuracy. So, we need two important properties: number A, higher resolution, and second, the non-oscillation, non-oscillatory. So, that will actually lead to some different class of resolution scheme, and that we will have discussion in the follow up lectures. So, where you can see how we can devise higher order resolution scheme, but at the same time preserving the property of the non oscillation. So, that whenever you get an sharp gradient, the wriggles should not appear in the solution. Now, just to conclude these things, one more discussion we need to do is that higher order scheme on unstructured grid. So, how would that look like, the higher order scheme on the unstructured grid? So, if you see this particular stencil, this is an unstructured grid. So, this is your unstructured grid, and now here in this case you can see this upwind node C and F, and they are connected with the distance, and higher order higher resolution convection scheme we want to develop given the velocity at the face in this direction and other case in this direction. So, what is important is that how to find out the information at the upstream case if the phase velocity in this direction, and when the velocity in this direction, how to find out this point. So, for structured system this was easy to find out, but unstructured system is required some sort of an involvement. So, now how one can do that is that let us say whatever profile that we have developed for the structure grids, now we can extend and try to use the same thing for here. For functional, let us say we start with quick scheme, which is having a functional expression, the functional relationship. So, the functional relationship provides that phi phi is phi c plus 1 by 4 phi d minus phi u by 2 plus 1 by 4 phi d minus phi c. This is what we got from the these things. Now, you can approximate the gradients at C and F, where your direction dCF will be come into the picture, or xi direction that we have shown for the curvilinear system. Now, then what you can get, del phi c by del xi equals to phi d minus phi u by 2 delta xi, and del phi f by del xi it would be phi d minus phi c by delta xi. So, this is how you can get. Now, then phi f can be represented as phi c plus half of phi d minus phi c divided by 2 delta xi plus delta xi by 2 plus half of phi d minus phi c divided by delta xi multiplied by delta xi by 2, or one can write phi f equals to phi c plus half del phi c by del xi by 2 plus half del phi f by del xi by 2. So, one can get in this. Now, now you have this vector dCF between C and F. So, you can write the phi f equals to phi c plus half of delta phi c dot dCF plus half of delta phi f dot dCF, which is quite suitable used in the context of the unstructured grids. This only requires the information related to gradient at the location C and F location. As long as computation of these gradients is second order, this can also, the way to calculate becomes immaterial, and that gives higher flexibility as compared to the original formulation over unstructured grids. So, now this particular expression suggests that I can write phi f as A phi c plus b delta phi c dot dCF plus c delta phi f dot dCF. where A, B, C, these are constant and determined by equating phi phi to the profile obtained over structured grids. So, now the general discretized equation of this can be found once and then used in all subsequent derivative. So, now what we will do, first get this information A phi c plus B delta phi c dot d c f plus C delta phi f dot d c f, which is, one can write A phi c plus B phi d minus phi u by 2 delta xi by 2 plus C phi d minus phi c divided by 2 delta xi by 2. Now, you do some sort of an algebraic manipulations, so that you obtain phi f equals to A minus C by 2 phi c plus B by 4 plus C by 4 phi d minus B by 4 phi u. Now, you can, above expression you can use to calculate A, B, C. For example, second order upwind if you consider. So, one can find the profile in a, just assume second order upwind, then the phi f which is written here second order case, the phi f is 3 by 2 phi c minus half phi u, which will lead to the coefficients b equals to 2, c equals to minus 1, a equals to 1. So, the equivalent form of the SU scheme will be given that phi f equals to phi c plus 2 delta phi c minus delta phi f dot d c f. So, that is an equivalent system for second order upwind scheme. If you follow the similar procedure, one can find for others, and I am noting down the final expression for, let us say, upwind, it would be phi f equals to phi c. For CD central difference, it would be phi f equals to phi c plus delta phi f dot d c f. Second order already we have written, but still you can, for the sake of closure, you can put things together. Phi f equals to phi c plus 2 delta phi c minus delta phi f dot d c f. You have from, which would be phi f equals to phi c plus delta phi c dot d c f. Now, quick, you get phi f equals to phi c plus half delta phi c delta phi f dot d c f, and downwind scheme will get you phi f equals to phi c plus 2 delta phi f dot d c f. So, we have already seen how to calculate this gradient at C n. Now, the final one which can is that the deferred correction approach. So, this deferred correction approach or DC, which enable us to use higher order scheme. So, essentially that allows you to higher order scheme, and then which can be also written in a very flexible fashion. So, the method which is used on writing the convection flux. So, if you writing the convection flux at phase F for using higher order scheme, then you can write m dot f phi f equals to m dot f phi f upwind plus m dot f phi f higher order minus phi f. So, this is something comes as implicit, this is explicit. So, where u stands for upwind and HO is higher order scheme. By expressing the flux in this fashion, so the first term term in the right hand side is implicitly evaluated and the second term on the right hand side is explicitly evaluated. And while doing that, so one can express his m dot f phi f HO is nothing but m dot f 0 phi c minus m dot f 0 phi f plus m dot f phi f h r m dot f 0 phi c plus minus m dot f 0 phi f. So, which is equivalent to getting your flux C f phi c plus flux f f phi f plus flux V f, which is again implicitly evaluated and this is explicitly evaluated. And what are the terms? The terms which are there, we can see the flux C f equals to m dot f 0 and flux C f equals to minus m dot f 0 and flux V f equals to m dot f phi f h r minus flux C f phi c minus flux f f phi f, like that. So, now we can substitute this one and put back and get the discretized equation, but we will stop here today and final discretized equation we can obtain in the next lecture. Thank you.